Yeah, so I'm your session chair. My high school teachers are not in the audience. Yeah, I liked physics and math because you could get the right answer even if your teachers didn't like you. So I was one of those. They wouldn't have been here. All right, anyway, so I'm here to introduce our first speaker. Grant Remmen is a James Arthur postdoctoral fellow at NYU, specializing in quantum field theory, scattering amplitudes, particle physics, general relativity, string theory, and cosmology. He was previously a fundamental physics fellow here at the KITP at UC Santa Barbara and a Miller fellow at UC Berkeley. He is answering the question, what is quantum field theory?
Thanks. Yep. All right, so I'm really excited to talk to you today. So indeed, I'll be answering what is quantum field theory, and the answer in the title of my talk is that quantum field theory is the language of theoretical physics. It's interesting because the man on the street has heard of quantum mechanics, has heard of string theory, has probably heard of relativity, but the general public as a whole has not really heard of quantum field theory, and it's not appreciated just how powerful of a theory this is, even among people outside of particle physics within the physics community. And so just in brief, before I actually get into the technical part of the talk, there are many answers I could give to what is quantum field theory, but it is the true quantum and relativistic mathematical formulation of particle physics. So if you really want to know what does the job of a particle physicist look like on a day-to-day basis, it is doing quantum field theory in various guises. And I should also add, it's not just a single theory, in the same sense that quantum mechanics is not a single theory. If you put an electron in a square well or a different shaped well, it's not a different theory, but a different model. In the same way, there are many different individual quantum field theories, and we'll talk about some examples in this talk. But quantum field theory as a whole is this broad set of ideas about how to make classical fields quantum mechanical. I should also add, it's in a sense the marriage of two giant pillars of physics from 100 years ago, quantum mechanics and Einstein's special relativity. And it's the culmination of really decades of mid-20th century physics, whereas relativity was sort of the work of essentially one person, and quantum mechanics was a large group, but relatively few at first. Quantum field theory was the work of many people over quite a long time, and it took really decades to understand what this theory is about. And before I get into this, one other thing to know about quantum field theory, it is the most precise and successful description of the universe that mankind has ever achieved. So in some sense, it is the definitive, intellectual achievement of humanity, if you like. Not to be too grandiose, but just to just to give an example of how precise quantum field theory is in describing literally the real world in a way that is testable, consider something called the anomalous magnetic moment of the electron. So the electron is a particle that has some spin, right? And so we could define some ratio between its magnetic moment, which is a vector, multiplied by the mass, divide by the charge, and divide by the spin. So this is a dimensionless number, and it's something we can measure in nature. So G over 2 is, I'm going to tell you the theory value first, just to show you how accurate this is. 5, 9, 6, 5, 2, 1, 8, 2. And so this is theory from quantum electrodynamics, and experiment is this. So this has been measured 1. So to within 1 part in a trillion, which is like predicting from first principles the distance from Santa Barbara to New York City to within about 1/10 of a human hair. So that's pretty impressive. Right. So let's get into it. So first, so this is going to be the rough overview of this talk. I'm going to try and give you a relatively complete and honest introduction to what quantum field theory is, I will be mostly actually following a wonderful textbook written by a UC Santa Barbara physicist, just up the alley there, Mark Srednicki. So if you're interested in actually learning quantum field theory for real at graduate student level, that's one of the great books to go to. So first, let's do a lightning review of quantum mechanics and special relativity, because we're going to be putting these two together in this talk. So the Schrödinger equation of quantum mechanics is the following. I times h bar, that's Planck's constant, over 2 pi, ddt of psi, so this is some vector, equals h psi. So if you've seen the Schrödinger equation before, you've probably seen it written in terms of psi of x, the wave function for, say, a particle in a box, and where you square psi, that gives the probability of finding the particle at that location. But here we're going to be slightly more general. We need not think about psi as just being some function on a line. We can think about it as a vector in some space that we call Hilbert space. So it can describe any system, not just a particle in a box. It could describe a spin interacting with a magnetic field, or almost any system you can imagine. So for a free particle on a line, h here is just what you've probably seen before, h bar squared over 2m d squared dx squared. And then if there's some potential, you add some potential term. So a thing to observe about this is that t and x appear differently. There is one derivative of time in the Schrödinger equation, and then position appears in kind of a complicated way in the Hamiltonian. It appears as a second derivative here, but it also appears in some position dependence in the potential. And that should give us pause, because special relativity teaches us that time and space are, on some sense, interchangeable. They should appear on more or less equal footing, and that is very badly broken by the Schrödinger equation. So what the heck is going on? And people struggled with this for quite a long time. There were at first attempts to modify the Schrödinger equation. And these carry various names, the Klein-Gordon equation, the Dirac equation, etc. But all of these examples, which I'm not even going to bother to show you, are just particular examples of quantum field theories. So we're going to talk about quantum field theories in general shortly. But first, let me remind you about special relativity. So in special relativity, so we're not going to be talking about general relativity in this talk. We'll save gravity for Rachel Rosen this afternoon. But in special relativity, three-dimensional vectors in space are upgraded to four-dimensional vectors in space-time. So we write them with Greek indices like this. So we have t, x, y, and z. These are so-called four vectors. And just to remind you how Lorentz transformations work, if you have some position in one coordinate system, and then you want to change to a coordinate system moving at some velocity v with respect to the original one, you multiply your original coordinates by some matrix, lambda. So here, every time you see a repeated index, here nu is repeated, you're meant to sum over repeated indices. This is so-called Einstein summation notation. And here, lambda is just the following simple matrix. So we're going to define gamma minus gamma v over c squared, 0, 0, minus gamma v, gamma. I'll tell you what gamma is in a minute. Okay, we're here. Gamma is the so-called gamma factor, very creatively named, in GR, or in special relativity, and it's 1 over the square root of v squared over c squared, where c is the velocity of light. Okay. This looks rather cookbook, but you can derive this very simply. And a nice thing about Lorentz transformations is that if all the indices are contracted, the object is Lorentz invariant. So x squared, so anytime we take some vector quantity and square it, what I really mean is g mu nu x nu. This will be just minus c squared t squared plus x squared plus y squared plus z squared. And the cool thing about this is if you transform t, x, y, z according to this Lorentz transformation, x squared is unchanged. It is so-called Lorentz invariant. It is something that does not depend on what reference frame you're in. It's unchanged when you move. So here, g mu nu is what's called the metric. And it's minus c squared, 1, 1, 1, with zeros on the diagonal. So this is literally the object that is defining distances in space-time. Time is, in a sense, negative norm distance relative to space. And in GR, the metric becomes dynamical. Okay, so from now on, we're going to set units of c equals 1. As we'll see throughout this talk, we will continually define various units to 1 in ever-increasing levels of abstraction. So this is the first time that happens. All right, so any questions on the first bullet point here, quantum mechanics and special relativity? Okay, great. So we've just covered the two revolutions in the first, 10 minutes of this talk, of the first 20 years of the 20th century, 25 years. All right. So now I want to talk about oscillators and algebra. And I want to just look at the case of the simple harmonic oscillator. So we have some potential, V of x. It's just going to be a parabola. So you can think about this like a particle on a string, or like a pendulum swinging back and forth in the small angle approximation, or you can find this in various circuits. It's a universal feature of physics that sort of everything wiggles, right? So everything, any potential looks near its minimum like the simple harmonic oscillator. So what is the Hamiltonian? The Hamiltonian here is just going to be the momentum operator squared over 2m plus 1/2 kx squared. So this is the kinetic term, and here's the potential. So here k it's the spring constant, right? So m omega squared. And p here, this momentum operator, is just going to be h bar over I ddx. So squaring it, dividing by 2m, gets you the usual kinetic term that you have in the free particle Hamiltonian. All right, so we could ask, what are the solutions of the Schrodinger equation? So we have a particle in a quadratic well. What are its ground states and excited states? So I could draw what the wave functions look like. The ground state looks like this, and then there are various excited states, etc. But all I'd be doing is just solving the time-independent Schrodinger equation. H psi equals E psi, or H times psi of x equals E times psi of x for some E's, and we have to find the eigenvalues. So the solutions are actually well known. Psi n of x is just, I'm going to write it for you just to show you that it can actually be done in closed form. That's not always the case. Omega over pi h bar 1/4. So there's this famous exponential, which makes the wave function die off as you go to infinity, which you should kind of expect. Times, and there are these fancy polynomials, the so-called Hermite polynomials. M omega over h bar x. So Hermite polynomials are just a set of polynomials that the mathematicians know and love. You can look them up in tables, but it sort of doesn't matter because ultimately the wave function dies off at infinity. And so this is why the ground state looks like this. The first Hermite polynomial is just 1, so it's literally just a Gaussian. And the fact that it's a Gaussian, and the energies, I should write down the energies. The energies are in units of h bar omega, and it's n plus a half. So this half is famous because this means that the ground state does not have zero energy. There is unavoidably energy in the ground state of a half h bar omega, and in a sense, this is hiding one of the central mysteries of quantum field theory and quantum gravity, which is the cosmological constant problem. If you ask about the zero-point energy of every single quantum field in the universe, and you add up all the zero-point energies, you get something infinite. We've measured the cosmological constant since the late 90s. It is not infinite. It is, in fact, very small. And what is canceling off all the zero-point energies of all the fields in the universe is a major open question. But you can roughly think about why there is zero-point energy as related to the uncertainty principle, right? You have localized a particle somewhat. So but not entirely. So there's some uncertainty in position, and there's going to be some uncertainty in momentum. Okay. From now on, since I've been writing an awful lot of h bars, we're going to set h bar equals 1 from now on. This isn't totally arbitrary, and there's still a sensible way of counting units when you set h bar and c to 1. So first of all, choosing c is literally just a choice of units. Nature doesn't care what a meter is or a second is. We're just going to measure time in meters, in effect, or meters in seconds. Setting h bar to 1 is like choosing a mass scale. So from now on, 1 over distance will have units of mass, or energy. So this is very convenient particle physicist way of thinking about units. Okay, good. So now in quantum field theory, so I complained earlier that t and x appear differently in the Schrodinger equation. So what we're going to do is we're going to demote position, right? Because position is an operator in quantum mechanics, but time is a label. So we're going to make position like a label, just like time in quantum mechanics. Because in quantum field theory, you can really think of quantum field theory as just a set of oscillators at every point, a set of simple harmonic oscillators at every point in space. So here, this is this direction is field space, and they're all coupled to each other and talk to each other. And this isn't so unfamiliar. If you think about a violin string, and you think about the position of the violin string above and below equilibrium as defining some field, you now have a field variable at each position along a one-dimensional field theory. And so talking about how waves move on a string is literally a classical field theory, and you could quantize that, and that would be a quantum field theory. That's actually how you can derive string theory, but that's another talk. Okay, so quantum mechanics is, or quantum field theory is the quantum mechanical description of this infinite system. How do the different oscillators affect each other? And for that, we need one more piece of technology from classical physics that you might have seen in your undergrad days, which is Lagrangians. So I'm going to give a lightning review of Lagrangian mechanics now. Okay. So physics can be described by something called an action, which we often write as S, as an integral from T1 to T2 of some kinetic energy minus some potential energy, here integrated over time. So the prototypical example to think about is just 1/2 m v of t squared, and with potential mg h of t, right? Because then, if you forget Newton's laws and you just say that nature demands that this action be minimized for whatever trajectory the particle traverses, you can compute the variation of the action, and it will just be minus the integral from t1 to t2 of m v of t a of t, a is dv dt, the acceleration, plus mg v of t dt. So demanding that is 0, so that the action is minimized, you get that a equals minus g. The particle is accelerating downward at constant rate due to gravity. So here, I got this just from putting in the right kinetic energy and potential energy into the action, no need for Newton's laws. And this is a general feature of the so-called Euler-Lagrange equations. And it's completely equivalent to classical Newtonian physics. And there are many problems that you can imagine are easier to solve if you don't spend your time keeping track of forces on every single part of the system, and instead just treat it in terms of energy. So in field theory, Lagrangians here, so this is L, a Lagrangian, get upgraded to Lagrangian densities, because we're going to be integrating not just over time, but over space. So we write Lagrangian densities with a fancy curly L. And a nice example is just a scalar field theory. So minus 1/2 d mu phi, d mu phi. So here d mu, this is relativistic notation, dt, dr, d theta, d phi, minus 1/2 m squared phi squared. right? So if you now demand that dl d phi equals 0, and you keep track of variational derivatives in the right way, you get exactly that box phi minus m squared phi equals 0. So here box is just d mu, the Laplacian. So this is the Klein-Gordon equation. So Klein and Gordon, this was one of the attempts to generalize the Schrodinger equation to make it relativistic, but instead of positing this equation as some fundamental property of nature, this is just the classical limit, the classical output of just the Lagrangian for a free massive particle. So now we're in business, because now we could think about any potential we like, or we could add multiple different kinds of scalars and have them talk through various kinds of interactions. And that is exactly what quantum field theory is, and that's much of what particle physics is trying to figure out what is the fundamental Lagrangian of nature. And you might have seen the Lagrangian for the standard model of particle physics on various shirts I've seen walking around here that one can buy at the LHC gift shop. And indeed, that is the central achievement of particle physics over the last 100+ years since we first discovered the positron and the electron and all that. Okay, good. So now, complementary to the Lagrangian is the so-called Hamiltonian description of physics. So if I define momenta as dl dq dot for general coordinates q, I can define a Hamiltonian as the sum of pq dot minus the Lagrangian density. And so Hamilton's equations are just dq dt equals dh dp, and dp dt equals minus dh dq. So these are equivalent to the Euler-Lagrange equations, and we'll find it convenient occasionally to pass back and forth between them using this so-called Legendre transformation. Okay, this is also entirely equivalent to standard Newtonian classical physics. So you might be wondering at this point, I've been saying that nature likes the particle to take the path of least action, and I've been demanding that the variation of the action vanishes. Why is that? Why is classical physics equivalent to some least action principle? And it's because really what's happening is that nature is performing something called a path integral. So we're integrating over all paths in field space of some action e to the is. And you can compute not just the classical paths, but you can look at all possible variations of the system from some point in state space to some other point. So there's all these possible variations. And all of them, except the classical trajectory, get phases, get imaginary phases here that, roughly speaking, cancel out. And so in everyday life, you see all the objects around you obeying classical equations of motion because all of the quantum phases of all the other possible paths have destructively interfered. And so the central objects then of study in quantum field theory are path integrals. And we'll be trying to understand those quantum corrections because sometimes those quantum corrections, even though they're tiny, can matter and be detectable. So we're now going to be doing quantum mechanical path integrals before then upgrading that to quantum field theory. Okay, doing all right on time, I think. Any questions? I know this is super fast, but I'm wanting to really show you all of the intellectual steps that get you from classical mechanics all the way to quantum field theory. Okay. So, right, quantum mechanical path integrals. So we're again going to start with our friend the Hamiltonian, 1 over 2m p squared plus some potential v of x. Where here x is again an operator because we're in quantum mechanics. So we want to know what is the probability amplitude. So the amplitude is going to be roughly the square root of the probability. What is the probability for finding a particle to be at position x1 at time t1 and position x2 at time t2? So we are going to dot x2 into the e to the I h t2 minus t1 dotted into x1. So this is what you get if you were solving the Schrodinger equation. And you can show, if you go to a so-called Heisenberg picture, where we make x time dependent by dotting it on both sides with e to the iht, that x2 t2 dotted into x1 t1, this probability, is going to be just this path integral. dx e to the I integral from t1 to t2 of our Lagrangian dt, where the Lagrangian is just p times x dot minus our Hamiltonian. Good. So similarly, if I wanted to compute something slightly more sophisticated than just what is the probability for the particle to be at this position at some time, if I wanted to instead compute some average of variables x at time t prime, x at time t double prime, x2, t2, and for technical reasons this is going to be some time-ordered product, I would get just that I'm taking some path integral over dx of and dp of let me just erase this, of x of t prime, x of t double prime times e to the is. So you can see the idea here is if you're trying to compute some expectation value of some observable, you do that path integral with those observables jammed into the path integral. All right, and compute the integral over all possible paths. So these integrals are somewhat annoying to compute in general, but there's a cute way of making it much simpler, which is to add what looks like some fictitious force. So define your Lagrangian in the normal way, but then add some forcing term, like some external force in x and some other external force in p. And then what you can do is you can take derivatives with respect to f and h, with respect to the external forces. So if I'm trying to compute some observable x at t prime, and maybe I care about the momentum at some time t double prime, what you can do is you can just differentiate by f at t prime, differentiate by h at t double prime, and act on just the plain old amplitude that we computed in the first place, but evaluated f at f and h equals 0. So it's a convenient way of doing that integral. So now we're going to do the same thing with quantum fields. Okay. So far this is just quantum mechanics. This is just computing various observables in a quantum mechanical system, but I've introduced all this fancy mathematical technology because it will make our lives much, much easier when trying to do this for quantum fields. So we can define a Hamiltonian for some quantum fields, d3x of, so I'm going to define some operators a dagger of x times minus 1 over 2m d squared of a of x. Or I could think about that in momentum space in terms of some a tilde of p, a of p times, I should have written in here, just p squared over 2m. Because you can recognize this as the p squared over 2m operator. So here, a tildes are just the Fourier transform of the a's, right? So you take it, the a, you multiply it by e to the minus I p dot x, and you integrate over x space. So these a's, which are, by the way, called creation and annihilation operators, it sounds slightly mysterious at first, but what all these things do, they're quantum mechanical operators that they act on the vacuum and they create a particle. So they satisfy some nice set of nice algebra here. A of some momentum p, a of some momentum P prime. If I compute their commutator, which means this times this minus this times this, that vanishes. And on the other hand, if I dagger one of them, then I get just a delta function. Okay. So something we can do is we can make our phi operator, our field operator in x and t, we can make it Lorentz invariant. We can write it as d4p times, we're going to put in some function that only selects positive energies, times delta 4 of p squared minus, or plus m squared. So this is imposing that the momentum squared equals minus m squared. That means that the momentum is on shell. That means it's satisfying the classical requirements of energy. We can multiply this by just a of p e to the I px plus a dagger of p e to the minus I px. Right? So that is some quantum field theoretic definition of my field operator for phi. If I insert the field at some position and time, I can think about that as inserting a bunch of these creation or annihilation operators in momentum space. Good. And so now a multi-particle state, if I have some multi-particle state of a bunch of momenta, k1 through kn, I can just act on the vacuum with a dagger of k1 all the way through a dagger of kn, acting on the vacuum state. Good. So now, at last, we are equipped to start computing scattering amplitudes, which are precise quantum observables within quantum field theory. And what do I mean by precise quantum observables? So you know from the uncertainty principle that trying to confine a particle to some very particular location or very particular momentum messes up your other observables. If you pin it down to one location, you don't know anything about its momentum, and vice versa. So really, quantum mechanics doesn't like local observables like that. What quantum mechanics likes are observables where you define a bunch of stuff going in at long distances, a long time ago, what we call past null infinity. So particles come in, stuff happens, and particles go out. And this is literally what scattering amplitudes do. We do not care what happens in the middle. We ask, because it's indescribable in terms of local, classical, intuitive degrees of freedom. Instead, we have to just simply describe, if I put in some particles at long distances, so if I turn on the LHC and I have some bundle of protons shooting in, a bunch of messy stuff happens, and my detectors are, meters away, which in quantum mechanical terms might as well be light years away. And I measure some Higgs bosons, I measure some gluons and some quarks, and that's coming out at very long times and very large distances later, relative to the scale of the interaction. So we started thinking about scattering amplitudes as a particle physics community for very pragmatic reasons. It's literally the thing you measure in accelerators, but it also makes sense from these fundamental quantum mechanical reasons because it's not a very local observable. It's sort of a maximally non-local observable, if you like. So what these are, formally, is some final state dotted into some initial state. So in particular, it's the vacuum here, and then I'll have some time-ordered product of a bunch of annihilation operators acting on the future. So here, let's just do 2 to 2. A1 prime at plus infinity, A2 prime at plus infinity, and then I have A1 dagger acting on minus infinity, A2 dagger acting on minus infinity, and again acting on the vacuum. So this is just describing two particles coming in, two particles going out, and for whatever Lagrangian describes our field theory, we want to compute this. So using some of what we've just developed here, we can actually write down formally what this is. And this goes by a very fancy name, the Lehmann-Simanzik-Zimmermann reduction formula, so LSZ reduction. And all it is just the following. So you have some factors of I, because there's factors of I all over the place. So we're going to integrate over the position of particle 1, e to the I k1 x1. And then we have something that's going to keep us on shell. So it's going to demand that the external particles have sensible momenta. And then d4 x1 prime of e to the minus I. So this is for the outgoing particle, k1 prime, x1 prime. The Laplacian acting on the 1 prime particle, m squared. And then the same for the second particle times just some time-ordered product of just a bunch of field insertions, phi1x, phi x1 prime, etc., acting on the vacuum, where these are literally just what we defined here in terms of creation and annihilation operators. So this is formally what amplitudes are, and so all we really have to do is we boiled the problem of computing observables in quantum field theory down to just computing these time-ordered products of a bunch of field insertions. And those go by the name of scattering amplitudes. So now we're going to use all that somewhat painful path integral technology I developed earlier and try and see if we can get all the way to Feynman diagrams in the next few minutes. So, okay. Any questions before we do that?
Yeah, I have a question about the B function that you had in the path integral formulation.
Yeah.
Can you say a little bit more about that?
Yeah, so yes, there are lots of different D's appearing on the board. That's I think there's been at least 4 so far. So you're talking about this D that appeared in the path integral measure. So this is the integral measure over all possible paths. So all possible choices of configurations of paths in field space. So this is, I'm integrating over, if I have a single particle on a line, I'm integrating over all possible positions of that particle as a function of time. For fields, it's much more complicated. I'm integrating over all possible values of the field, integrated over, all possible values of the field at each position in time and space. Yeah. There are formal mathematical ways to define this, but I'm not going to do that in this talk.
And sorry, one thing. Awesome. We have a few people joining us on Zoom, and your questions are interesting, so we want them recorded. So we would like to get you the mic. If you raise your hand, we'll bring you the mic if you want to ask a question.
Good. So now let's define the path integral. So we're going to define it in terms of J. So J here is some source term. It's going to play the role of, do you remember those forcing terms I introduced a few minutes ago that were helping us to compute the path integral in quantum mechanics? The exact same thing appears in quantum field theory. So here we're going to do some path integral over a field space of phi of e to the I d4x of some Lagrangian L0 plus L1 plus J phi. All right, so here L0 is going to be the kinetic term, the action that generates Klein-Gordon, so maybe a mass term if this is a massive field. And L1 are the interesting interaction terms, phi cubed, phi the fourth, etc. So the Higgs boson, for example, has a Lagrangian more or less like this. It has a kinetic term, a mass, and some cubic and quartic terms. So this is, except for the fact that the Higgs is complex, this is literally what they're computing at the LHC for looking at scattering of the Higgs. Okay, so now I could define, I would find that z of j equals up to some normalization e to the I d4x of L1 evaluated at 1 over I d dj, right? So we're again differentiating by our forcing term acting on z0 of j, where z0 of j is just e to the I over 2 d4x prime of the force term times what's called a propagator. So here, this delta force term is just defined as the solution of the following equation. So delta is really just what's called a Green's function. So it doesn't have a closed form solution, but you could imagine integrating this to find some function. Okay, so how to organize this computation is a massive combinatorial problem. Why do I say that? Because if L1 is, say, phi cubed or phi fourth, like the Higgs, here we're taking functional derivatives with respect to J 3 or 4 times, or more if the potential is more complicated. So as you know, when you start taking multiple derivatives, it becomes kind of a combinatorial problem. Do you act with multiple times on one term, or do you act multiple times on one term and then some other number of times on another term, etc.? It's just a bunch of instantiations of Leibniz's rule. And how to organize this massive combinatorial problem was figured out by Richard Feynman, and then explained to everybody by Freeman Dyson. Because at first nobody understood what Feynman was talking about, but Dyson was really a champion of these diagrams. And so it's called Feynman diagrams. You've probably seen pictures of these before, but they're not just pretty pictures, they are actually ways of organizing a computation. So the idea is to draw all graphs associated with the interactions of the Lagrangian. Then you send all derivatives to IP, because you're going to Fourier transform, and momentum space is much more convenient. Each vertex gets a factor of n factorial times gn if it's some n-point vertex. Each internal line gets a propagator, so a factor of I over p squared plus m squared minus I epsilon. So this is just the Fourier transform of the Green's function. And then all loops get integrated, and this is the real painful part. Anytime you have some internal loop, you have to integrate over momenta times 2 pi to some power. And then finally, you multiply it all together, and it gives you exactly this fi amplitude that we care about, up to various factors of 2 pi and delta functions that we're not going to worry about. So let's do an example Feynman diagram in a nice simple scalar theory, so I can show you how this works. So now we've gotten to really what daily life looks like for many particle physicists, which is computing Feynman diagrams for some model of interest. If you were tasked with making predictions at the Large Hadron Collider, if you were one of the phenomenologists in, say, ATLAS or CMS, one of these major multi-thousand person collaborations at the LHC, your central task oftentimes would be computing Feynman diagrams to then match onto experiment. And I'm going to do this in a very simple example, but trust me when I say that some of these theories are very hard to compute the Feynman diagrams for, because once you start having spin, things get more complicated. Once you start having to go to high loop level, things get very complicated, and people will spend their entire lives specializing in how to compute particular multi-loop diagrams. And there's a whole reformulation of quantum field theory that Arkani-Hamed and company have been championing lately, in which all of the integrations over off-shell momenta get replaced with contour integrations over complex but on-shell momenta. So you trade one difficulty for another. Integration over loop momenta with complex contour integration. But I won't have time to say anything more about that. But okay, let's consider the following example theory. So again, a scalar and another scalar that we'll call x. And phi will have some mass little m, and x will have some mass big M. And then we're going to have some interaction term, g phi squared x. All right. So now let's look at the diagram. So I'm going to do dotted lines for phi and solid lines for x. So we have to write down all possible different topologies. So here I'm interested in phi-phi scattering. And then there's one more topology where the lines kind of cross under and over each other. Okay, let me define a couple of things. These are so-called Mandelstam variables. So S is just going to be P1 plus P2 squared, so squared in the 4-vector sense. T is going to be P1 minus P1 prime squared. So primes are for the outgoing momenta. And then U is going to be minus P1 minus P2 prime squared. All right, so we have 1, 2, 1 prime, 2 prime. And this is a so-called S-channel, T-channel, and U-channel diagram. Yeah.
Can you explain how you're getting those topologies? Like, how do you know how many fields go in and out of a vertex that might?
Yeah, sure. So here I've just chosen a particular process I want to compute. I want to say, which I can pick arbitrarily. I want to say I'm going to choose to send in 2 phi particles. I'm going to post-select on 2 phi particles coming out, and that's what I want to measure the sort of probability for that kind of interaction. Okay, so now we can see these are just kinetic terms. These are just mass terms. So these are taken care of just by propagators. The only interaction in this theory is this, which gives us a cubic vertex because there are 3 fields that talk to each other. So the fundamental interaction is 2 phi fields and 1 x field. And the Feynman rule for it is very simple. It's just 2ig. 2 because 2 factorial is 2, and there are 2 phi fields and 1 x field. So this is just what you get from running through the Feynman rules, which are nice ways of packaging the very painful combinatorics of trying to do the path integral directly. And so you can compute the scattering amplitude for this. So every time you see a vertex, you get a factor of 2ig. Every time you see a propagator, you get one of these guys. And you put them all together and you add them up. And what you get is that I times the amplitude is just 4ig squared. 1 over minus s plus m squared minus I epsilon, plus the same thing for t, plus the same thing for u. So this is an example of an honest-to-goodness quantum field theory calculation. This would normally have, you'd probably get to this after about a week or so of grad school QFT. But this is probably the simplest quantum field theory. And cross-sections, these are more physical objects. So cross-sections are just the squares of amplitudes. So if you have a bunch of particles, say, that are bouncing off each other, and you have some number density n, so 1,000 particles per meter cubed, and if they have some mean free path lambda, so some average distance lambda before they hit each other, you can think about that as a cross-section, the effective size of the particle seen by this interaction, sigma, is just 1 over n lambda, which you can check has units of meters squared, right? So it's an effective size of the particle. And scattering amplitudes give you cross-sections. In particular, if I define some differential solid angle as sine theta, d theta, d phi, then d sigma, d omega is just up to, again, there's always factors of pi squared times momentum, 1 over 1. It's just the amplitude squared. So that's what cross-sections are really computing. How much time have I got? Okay. Oh, we're doing fine then. Okay. Great. So what I now want to do, so that was a so-called tree-level computation because the graphs, there were no loops in any of the graphs that I've now erased. But a lot of the non-trivial properties of quantum field theory arise at loop level. Because on some level, tree-level graphs are secretly telling you about classical physics. You can think about them as just taking a bunch of plane waves, letting them interact, and then just solving the classical equations of motion at leading order in the interaction strength. But if you really want to get at the quantum part of quantum field theory, you have to go to loop level. So we're now going to talk about running and renormalization. So where the constants of nature turn out to be not so constant after all. So a fact of life is that these loop integral diagrams often diverge. And people worried about this for a long time. Any sensible theory shouldn't give us infinities. But it turns out there's a nice way of sweeping away the infinities, but the cost of doing so is making the constants of nature depend on energy scale. And this turns out to be central to quantum field theory. In fact, I think, Flip, you referenced this in Joe's paper. If you read the abstract of his paper, he referenced Ken Wilson's work on quantum field theory. And Ken Wilson's central insight was that quantum field theory indeed shouldn't be thought of as being organized by graphs of different topologies, but should be thought of as being organized by energy scale. So that's what we're going to sort of focus on now. So we're going to consider a scalar with a quartic interaction, as always. So again, this is something very, very much like the Higgs boson. So we have a kinetic term, we have a mass term, and then we're going to have some quartic term that for traditional reasons I'll call lambda. So we have some 4-point interaction. Now, I want to work in d dimensions, not just in 4 dimensions, not because I'm trying to do anything stringy involving 10 or 26 dimensions, but because in exactly 4 dimensions, these integrals will diverge. But if I pretend that dimension is just a number, right, not necessarily 4, 5, 6, but a real number, then I can move slightly away from 4 dimensions, find that the integral is finite, and then find ways of sweeping those infinities away. So the technical term for this is dimensional regularization. It is one means of dealing with the infinities and scattering amplitudes. There are many such choices are called renormalization schemes, which makes it sound slightly nefarious, but I assure you it's not. Right, okay, so we're going to work in d dimensions. So a fact about actions is that the mass dimension of the action, so here I'm going to use square brackets for mass dimension, the mass dimension should vanish because they're just numbers, right? We get e to the s, and you can't take e to the meters or e to the kilograms. They have to be just numbers. So s should be 0, the mass dimension, which means the mass dimension of the Lagrangian density should just be d, right? Because you integrate the Lagrangian density times d factors of space and time, which go like 1 over a mass. So in order for the mass dimension of S to be 0, the mass dimension of L should be d. Mass is mass. So the mass dimension of phi is just d minus 2 over 2, just by simple algebra. Okay. So in 4 dimensions, phi has units of kilograms. In 5 dimensions, phi has units of kilograms to the 3/2, etc. That's just life. So we can ask, what's the dimensions of lambda? In 4 dimensions, lambda is just a number. It's a coupling constant. But in d dimensions, it's some coupling constant that carries units with it. So in d dimensions, lambda has units of 4 minus d. So that means we should really, if we want lambda to be massless, we should replace it by an honest-to-goodness mass-independent lambda times some mass scale to the 4 minus d dimensions. So here I've just pulled out mass dependence so that lambda is just a number. Make sense so far? Just dimensional analysis. Okay. So now I'm going to show you how lambda will run. And this is the particle physics term for a coupling constant that depends on energy scale. Before I do that, let me give you a little bit of intuition for why this should happen. So think about electric charge. I know, different theory than we've written down, but it's a bit more familiar. So if you have some electric charge, and it has some field strength lines going out, you could measure that charge by placing putting the particle in a box and integrating up the field over some Coulomb box, right? Now you could imagine doing that for spheres of arbitrary size and you'd still measure the same charge. But that's not true in quantum field theory. Because in quantum field theory, you don't just have the electrons sitting there, but the vacuum itself is roiling with electrons and positrons popping in and out of the vacuum. Traveling a short distance and then annihilating each other. This is sort of a cartoon for what's really going on, but it will suffice to make the point. So you have these little electron-positron pairs popping in and out of the vacuum. What they do is they act like a dielectric, right? Because they're effectively little dipoles that can screen the charge a little bit, right? So this means if you have some finite charge that you're measuring at infinity, where you've got an infinite number of dipoles between you and the electron, then as you move in closer and closer, the charge is being screened by fewer and fewer of these quantum dipoles, meaning the charge actually grows. So the coupling of electromagnetism gets larger at shorter distances. That's one example. The couplings of the electroweak symmetry, the couplings of QCD, quantum chromodynamics, for which David Gross here, a Nobel Prize winner, is famous for computing the beta function of quantum chromodynamics. They all run with energy scale because of effects like this. So we're going to see how this works quantitatively in this simple theory of a quartic. But that's the intuition. Okay. So let's ask, what is the one loop diagram that contributes to an effective 4-point interaction, right? Because how do we measure lambda? We define lambda just by the amplitude for 2 phi's coming in and 2 phi's going out, right? That's what this does. So that's the tree level diagram, and then the loop level diagram looks like this. Right? I still have 2 phi's going in, 2 phi's going out, but there's some loop in between. So that's one topology. But again, we have to consider all the different topologies. Let's see if I can draw this nicely. Right. So there's all the different topologically distinct diagrams at one loop. And you could go to yet higher loops if you wanted to, but we don't have time today. So let's compute these and see what they do to our quartic. Okay, so I'm going to define momenta K1, K2, P, P plus K1 plus K2, and compute this diagram. All right, so what we get is just reading off the Feynman rules in the same way as before, minus lambda squared, mu to the 4 minus d over 2 times the integral of d, so we're working in d dimensions, over 2 pi to the d, 1 over p squared plus m squared, 1 over p plus k1 plus k2, squared plus m squared. Plus the other channels. And by other channels, I mean just these two topologies that are basically the same thing, just with reshuffling of labels. So, do you see where this came from? We get lambda squared, right, because each insertion of a vertex costs us 1 factor of lambda. And now we're doing an integral over the internal momentum p, and we have the propagator here for this guy, times the other propagator for this guy. And you can see already why I went to d dimensions rather than 4 dimensions. Because if this is in 4 dimensions, I'm integrating over 4 powers of momentum. But I have, when p is large, I can ignore k and m. I have 4 powers of momentum downstairs. So I have a d4p over p to the 4th. And it looks like 4 times the integral of dx over x, which you know is going to diverge logarithmically, right? So this is going to be infinity in 4 dimensions. That's why we're going to d dimensions. Okay. So we're interested in not the k dependence. We don't really care about that because that will generate higher derivative operators that look like phi squared, d phi squared, etc. We're just interested in the quartic term, the effective contribution to the potential. So I can just look at the k-independent part of the integral. So let's do that. It looks like the following. Let's throw away lambda for now. I'll introduce it at the end. Mu to the 4 minus d of the integral from 0 to infinity of the ddp. So this is, I'm integrating over some d-dimensional sphere. So p to the d minus 1 dp over p squared plus m squared squared. And what you get, you could plug this into some computer algebra system like Mathematica, or you can look up in textbooks. It's just mu over m to the 4 minus d times gamma of 2 minus d over 2 times gamma of d over 2. Where here gamma, I've defined, who here has seen the gamma function before? Okay, awesome. But I'm going to define it anyway, just so we're all on the same page here. Gamma of z, it's just some special function. It's just the integral from 0 to infinity of t to the z minus 1, e to the minus t dt. And it has the nice property that gamma of n is n minus 1 factorial. So you can think of the gamma function as the natural extension of just the factorial function, but to the complex numbers. And a fact of life about the gamma function is that it has poles at 0, minus 1, minus 2, etc. So this is going to diverge if we were to plug in d equals 4, which we knew to expect. Okay, so altogether, we have the following effective contribution to lambda at one loop. We have 3 lambda squared over 2, so we're going to restore everything, 4 pi to the d over 2, mu over m. So this mu should be worrying you, right? Because this was some just arbitrary mass scale we pulled out earlier. It doesn't mean anything physical. And all physical quantities can't depend on some crummy units we just pulled out earlier. So that should be something that is of concern. But we're going to set, now let's set d equals 4 minus epsilon. So here's the regularization part of dimreg. Epsilon is something that we want to be small. So we're pretending dimension is a real number. It's okay because eventually it's going to be set to 0. And you can compute what this looks like in the small epsilon limit. 3 lambda squared over 32 pi squared times 2 over epsilon minus something called the Euler-Mascheroni constant. It's just about 0.57 times a log of 4 pi mu squared over m squared plus order epsilon terms. So this is infinite. What do we do? Well, okay. The Lagrangian that unfortunately I've erased was what's called a bare Lagrangian, right? It's our starting point. It's not necessarily physical. We don't measure, whatever nature knows as some true value of lambda. We just measure the effective value of lambda by scattering phi's. That's all we can do is do experiments. In the same way that we don't measure the bare charge of any object, we just measure the effective charge by measuring the electric force at some finite distance. So what we should do is we should take our Lagrangian, which is that thing I wrote before, but now we're going to call it L bare, and add to it something that's of order h bar times a shift in L. So in particular, we're going to add some shift in lambda, which goes by the name of a counter term. So we're adding in some other term that depends on lambda, some new d lambda times phi to the fourth, to soak up this infinity. And of course, there are choices for how much of the finite parts of this to soak up. We're going to use something that goes by the name of modified minimal subtraction, but that doesn't matter. So what we get is that lambda physical will depend on mu, right? Because I can soak up the 2 over epsilon with my delta lambda. I can also soak up the log of mu squared. So now what we get is that lambda physical is going to be, well, at this order in loops, lambda plus 3 lambda squared over 32 pi squared log of mu squared over m squared plus higher order terms. And what we really are interested in is something called the beta function, which is mu d lambda d mu. So how, if I multiply mu by 10, how does, that should be lambda, how does lambda change? So this is the derivative of our coupling in log mass space. And it's positive, it's just this. So if you integrated that, right, you would get that lambda is 1 over some constant plus a log, and you would find that, okay, this lambda is going to go to infinity at some mass scale. Now, you can't really trust the coupling constant when it's very, very large. Perturbation theory breaks down. But indeed, that's a signal that somehow the phi of the 4 theory is on some level sick. Its coupling diverges at some finite energy. But since I'm slightly running out of time, I want to move on to just have a bit of a conversation with you, since you're all teachers, about how to get into this line of research. If your students are interested in working in quantum field theory or becoming a theoretical physicist of any stripe, how can they do this? And you know, the path to research in quantum field theory and theoretical physics in more broadly is frankly narrow but doable. So I myself went to a public high school in a small town in northern Minnesota, and I mean I'm lucky in that I knew I wanted to be a theoretical physicist from a very young age. Ever since my mother bought me a copy of Kip Thorne's Black Holes and Time Warps for $1 at the library used book sale. You know, but if your students are really interested in becoming physicists, here's what they should do, in my opinion. They should start taking advanced math starting in around the 8th grade. If your school has advanced math tracks, that's really useful. As many AP classes as they can take in high school, in particular AP Calculus AB, maybe Calculus BC if possible. AP Physics, doesn't have to be calculus-based physics, can be algebra-based physics, that's fine. But it's important that they take the SAT and ACT, in my opinion. Especially if they do really well on it, this can unlock lots of scholarship opportunities, admissions opportunities at top colleges for them. They should also do the other usual college app activities, lots of other APs. The National Honor Society and volunteerism in general is really great. Music, theater, etc. Try to get top grades in all the AP classes. Also take the PSAT. I think that's still a thing, the PSAT for the National Merit. That is the way to get the National Merit Scholarship. And if students miss that window, they're kind of out of luck, so that's really important. But then in college, they should go to a good university, but it doesn't have to be Harvard or Yale. The great state universities, like where I went, the University of Minnesota, or indeed like UC Santa Barbara, are fantastic places to start out life as a physicist. It's useful to major in physics, obviously, but double majoring with math is also really useful for theoretical physics in particular. I myself did physics, astrophysics, and mathematics. In order to do all three, APs helped me get a lot in. They should take honors courses at their university if available. The honors programs are great. Undergraduate research doesn't have to be in theoretical physics. It's often impossible to do real research in theoretical physics as an undergrad because you haven't had the courses. So pursue other branches of physics. Astrophysics, for example, in my case. Do summer research once or twice, REU programs, or even abroad. And then, the usual things, top grades, letters of recommendation, take the GRE and get into grad school. And then after that, it's postdocs and hopefully faculty positions. But that's just a very, very brief summary of the life choices to get into theoretical physics, which no one ever tells high school students or even beginning college students what this looks like and what are the set of things you need to do. A lot of times students are left kind of figuring it out for themselves, or hopefully having really great teachers to mentor them. So hopefully that can help. In the last few minutes, any questions on the whole paths into theoretical physics? Yes.
So for students who don't go to a top public school or like a well-recognized private school, do you have any advice, or maybe like folks in the room who've sat on admissions committees for graduate schools? Right. How do they get noticed? How do they show like, no, I'm ready for this? Right.
So you're talking, for example, students who maybe go to some small liberal arts college for undergrad or something like that.
Yeah, or a CSU.
Yeah. Good. So for two-year university students, I mean, of course, you can transfer to the major land-grant four-year universities. This depends on the state, but I know some states even have special arrangements with certain two-year colleges to automatically admit students. Again, that depends on the state a lot. But in general, for students that find themselves at a university that doesn't have a ton of physics or a ton of research opportunities, this is where summer research can be really, really useful. So I mentioned the REUs. These are called Research Experiences for Undergraduates. It is a wonderful program run by the National Science Foundation, and it pairs undergraduates at universities all over the country with mentors at major R1 research universities to give them opportunities during the summer to do research. So I highly recommend that. There are comparable programs abroad. I did one in England called the Dean's Summer International Student Fellowship at University College London. There are other things like that all around the world. So encourage, if you're a mentor of a student at a smaller university or college, encourage them to do summer research somewhere. Yeah.
Maybe I can just add, the NSF pays you for the summer, so you actually get paid for the work that you do, which is really important for a lot of undergrads. Also, I'm pretty sure, last I checked, to do the REU, you have to be an American citizen. So if you have a student who's not an American citizen, they have to be a little bit more creative on how to get involved in research. And if they want to get paid through the NSF at an REU, they have to be an American citizen. Study abroad programs may be accessible to them, but also financially those have burdens as well.
Right. I should also say, even some domestic universities have things that are equivalent to REUs, but may go by different names. Just as one example, Caltech has something called SURF, which is Summer Undergraduate Research Fellowships, I think. So it's not officially an REU, but it's functionally the same kind of thing. So looking at that, too, can be useful. Yeah. Good. Yeah.
So yesterday in the workshop, we looked at data from CERN that showed two protons colliding and creating a slew of particles.
Right.
We were interested in muons. Everything you showed us on the board there, two questions, I guess. One, can you predict what kind of particles will come out of the collision? And then for the two muons, we didn't see them in every collision.
Right.
Can you predict what is the probability that we'll get two muons out of two protons colliding?
Absolutely.
Sorry, do you mind if I just interrupt?
Please.
I'm supposed to be chairing the Q&A. So it seems like we're moving to Q&A, and that's a very interesting question. For any future question, let's go to the microphone so people on Zoom can hear. But for this case, maybe you can repeat the question since you have a microphone.
Yeah, thank you. Yeah. So the question was, you guys saw some data yesterday about two protons colliding and potentially two muons coming out, but sometimes muons don't come out. And the question was, can you make a prediction for the probability of seeing two muons as the final state for a two-proton initial state? Yes, you can. I tried to avoid introducing fermions in this talk or vector gauge bosons for the sake of time, but everything I said about Feynman diagrams applies equally well to theories of fermions or bosons. And so what you would do, and this is literally what is done among the phenomenologists, which is the word for the theoretical physicists who make the nitty-gritty predictions for colliders, this is what's done by the phenomenologists at CERN. So you take the standard model Lagrangian, you read off the Feynman rules, and you compute scattering amplitudes for protons aren't in the standard model, right? Because protons are big kind of sacks of quarks and gluons. You compute scattering amplitudes for two gluons or two quarks coming in and two muons going out, or maybe two muons plus other stuff, right? So two muons plus jets of quarks and gluons. And yes, these are standard computations that are done. They are very, very, very messy looking, but if you are doing this on a computer, which is how this is done nowadays, it can be done, yeah. And indeed, the calculation, the basic calculation just at tree or one loop level for two gluons coming in and two muons going out, I think calculations of approximately that complexity can be found at the end of many graduate student courses on QFT. In fact, are in Mark Shrednicki's book. So he actually does some standard model computations near the end of the book. One other thing I want to say, just at the very end here, is to give you a sense of what are some open questions in quantum field theory, right? Because this is a subject that's many decades old at this point, but there's a lot that we still don't know. One is this idea of effective field theories. So quantum field theories, as we've seen, care a lot about energy scale, right? There's this sense of running, coupling constants. And nature cares a lot about energy scale. After all, you don't need to know nuclear physics to understand hydrodynamics, or maybe we'll see in Rachel's talk later today, general relativity is some effective field theory that's describing quantum gravity at low energies. Similarly, if you just have some basic interaction among 4 fermions, that's some effective field theory that breaks down at some energy scale and gets replaced by 2 fermions coming in and exchanging a W or Z boson and going out. And there's a set of mathematical tools that, again, was referred to on Flip's slide called effective field theory that was developed by Ken Wilson in the 60s. And it's this way of organizing quantum field theory into not fundamental theories, but effective theories at some scale. For example, you could have an effective field theory of the proton or mesons called the chiral-Lagrangian that then gets replaced with Yang-Mills and quantum chromodynamics at some high scale. But a major open question that I've worked on, and actually Nick, another speaker that you'll hear from, has worked on, is trying to understand what is the set of all Lagrangians that maps onto healthy effective field theories in quantum field theory. It turns out one can prove that certain Lagrangians are sick, certain signs of couplings are forbidden by axioms of quantum field theory. And understanding that the space of allowed effective field theories is a big open question. Even more worrisome open questions are almost existential. Why is the Higgs boson so light compared to the Planck scale? I mean, it's very, very heavy, don't get me wrong, but it's much lighter than the scale of quantum gravity. And that's weird because loop corrections of the sort that I've now erased suggest that the Higgs should have a mass that's way up at whatever cutoff of quantum field theory is, quantum gravity scale. So why is there that fine tuning that makes the Higgs so light? Why is the cosmological constant that I referred to earlier so light? These are all questions that get at some prediction of quantum field theory that's breaking down. And it's worrisome and interesting and exciting for research because we know we're on the right track. Quantum field theory is this incredibly successful theory. Its predictions have been tested, and it holds in almost every aspect of life that has in which it's been tried. So the funny sort of flaws in the theory are hinting at something new and exciting. And I think that's where I'll leave you here.
Thanks for the incredible talk. I was getting flashbacks to my first year of grad school. It was very fun. All right, are there any further questions for Grant? And maybe I can ask a quick question. Is someone walking around with microphones? Okay, great. There's a microphone floating. So if anyone has any questions, please raise your hand and we'll bring you the mic. Looks like we already have some.
So I really appreciate coming and taking the time, especially how you opened with the best measurement ever. So I was wondering if I was to talk about that in my classroom, as far as, okay, why is it that quantum theory, field theory, gives us a good measurement? What is going on that says, okay, classically, this is what we would see, but once we take into quantum, we see this, and this is the 30-second hand-waving argument to sort of show them how magical quantum field theory is.
Right, good. So first of all, why quantum field theory in the first place? Because one can show it is the unique way of combining quantum mechanics and special relativity in a way that doesn't break either of those two. But for the particular example that I showed you earlier, so that was the magnetic moment of the electron, right? So, okay, we have some electron and we have some photon coming off of it. And there's some interaction here that you can predict just classically, right? It's the charge of an electron. The electron has some charge, it has some spin, and if you just know its charge and its spin, you know its ratio, the ratio of the two, right? You could, if you just imagine that the electron is some ball of charge E that is that has angular momentum h 1/2 h bar, you would get that G over 2. Remember, I defined that magnetic moment ratio for the electron. You would get that it's just 1 classically. This is the classical prediction that should be exactly 1. This was predicted, I think, around 90 years ago. But then the corrections start at 1 part in 1,000, et cetera, and it goes on. And what do these correspond to? These correspond to higher loop diagrams. So, for example, if this is my fundamental Feynman diagram, what higher loop diagrams can I draw? I could draw things like this. So here, wavy lines are photons, solid lines are electrons. I could draw things like that. and I could draw yet higher topologies. I could draw things like 2 photons coming out. I could cross the photons. You'd have to draw all the different topologies. And drawing all possible Feynman diagrams, order by order in the loop expansion, and computing their effective contribution to this magnetic moment of the electron is what I mean by the theoretical prediction. That's what got me those, I don't know, 10 or 12 or 13 digits. So it's just doing this Feynman diagrammatic calculation. It's the exact same sort of calculation that we did for the phi-4 theory, where I computed the first correction to lambda phi-4. So doing that up to many, many loop orders is what gives you this.
Further questions?
So as someone whose background is chemistry, not physics, a lot of this math and like equations was hard to follow. This might be difficult, but could you summarize some of like the key takeaways that I would need to understand out of what you were saying that will help me understand the rest of what's going to be happening today?
Yeah, sure. Okay, so fundamental to quantum mechanics are harmonic oscillators. Quantum field theory is just what you get if you put a harmonic oscillator in field space at every single position in space, and then couple them, and compute, and then treat that as some infinite quantum system that still respects special relativity. And just depending on how you couple them, and depending on how many degrees of freedom you put, so how many oscillators you put at each point, that is all the data of quantum field theory, just how the oscillators couple and how many there are. And the tools for computing quantum observables, so the probability for example, for seeing 2 muons if 2 protons go in, the tools for doing that are called Feynman diagrams, and the way you compute them, and what you're computing are scattering amplitudes. That's the crux of the whole talk. The rest is just math.
Great, thank you so much.
One more, should we? Should we just talk to Grant a break, or?
Yeah, that
Okay.
sounds good. Okay, everyone, thanks for the great questions. If you have more, you can find Grant during the break. Yeah.
Thanks.
Thanks again.